All right, in this lesson, we're going to look at situations where Newton's second law applies. We've looked at quite a few situations in previous lessons where Newton's first law applies, what I call equilibrium situations. Either the object is at rest or the object is moving at a constant velocity. In either one of those two cases, the sum of the forces acting on the object is zero, and we can use that result, that sum of forces equals zero, to solve for some of the forces that are acting on the object. We can use it to solve for things like normal force, frictional force, a pulling force, whatever it may be in that particular situation. In this lesson, we're going to look at situations where the sum of the forces does not equal zero. So there is a net force acting on an object. The one thing to point out about Newton's second law is if there's a net force acting on an object, the object's state of motion must be changing, which means its velocity must be changing, which means there must be acceleration. So the technique to solve these types of problems is very similar to the technique for equilibrium, except for one main exception. In at least one direction, the sum of forces acting on the object has to be equal to the mass of the object times the acceleration in that direction. So sum of forces equals ma, Newton's second law. So let's look at a quick example problem to look at how this might apply. I'm going to stand in the elevator in Fairfield Hall. I have a mass of about 65 kilograms, and I'm going to ride from the first floor to the second floor. Now, there are three different types of motion that happen going from the first floor to the second floor. The first type of motion is the elevator starts from rest and accelerates upward with a constant acceleration, and we've picked 1.5 meters per second squared as that constant acceleration. The second state of motion is traveling between floors. In the elevator between the floors, the elevator moves at pretty much a constant upward velocity. Now, we don't know what that upward velocity is. We could figure it out, and I think I've actually calculated it before. It's not very fast. If you've ever ridden in that elevator, you know it takes quite a while to go from the first floor to the second floor. When we get to the second floor, we have our third state of motion, which is the elevator slows down until it reaches a rest on the second floor. Also an acceleration, a negative acceleration, and we're also going to say that that acceleration is also a magnitude of 1.5 meters per second squared, so negative 1.5 meters per second squared. Now, this 1.5 meters per second squared is not something I just picked out of thin air. It's actually something that's relatively close to the acceleration of the elevator. I've done this demonstration since Fairfield Hall opened, and this is pretty close to what the acceleration of the elevator really is. I can tell you the elevator does not accelerate for very long, maybe like a second, so the speed that you're moving between floors is pretty slow. So we're going to try to determine the normal force of the floor acting on me during all three different types of motion. The elevator is speeding up, the elevator is traveling between floors, and the elevator is slowing down. So let's look at the first part, the speeding up. So let's draw a free body diagram, my usual technique. Weight is acting down, normal force is going to be acting upward. I've also included one other piece of information, that the acceleration of the object, or the acceleration of me in the elevator, is 1.5 meters per second squared in the upward direction. I'm going from rest to some upward velocity. So if I take and add those forces together, the sum of forces must equal my mass times acceleration. So normal force minus mg, so how much the floor is pushing me up minus my pushing me down, has to be equal to my mass times acceleration. So if we solve this out for normal force is equal to ma plus mg. So normal force is equal to m times a plus g. So if I plug in the values, 65 kilograms my m, 1.5 meters per second squared my a, 9.8 meters per second squared, the acceleration due to gravity, I calculate a normal force of 734.5 newtons. Now, it's worth pointing out that this normal force is larger than my weight in this case. During this time of speeding up, I'm going to feel instantaneously heavier than what I actually am. Your perception of how much you weigh is actually not determined by the force due to gravity pulling you down, but rather the normal force pushing you up when you stand on a surface. So the second part is the constant speed part between the two floors. Acceleration is equal to zero. I still have my two forces, weight and normal force. And if I applied Newton's second law, I can run through the exact same set of algebra. Normal force minus mg equals ma. Normal force equals ma plus mg. Normal force equals m times a plus g. And so normal force is equal to 0 plus 9.8 times 65. So 637 newtons. Now it's worth pointing out that I could do part 2 also by saying sum of forces is equal to 0, since we know that the acceleration is 0, moving at a constant velocity, then sum of forces is also equal to 0. What this would mean is 0 is equal to normal force minus mg, normal force is equal to mg weight, and if we work it out, we'd see we get the same result. So in this case, the normal force of the floor acting up on me is equal to my weight. Now, it is also worth pointing out in this particular situation is that if I am riding in an elevator between floors, and I did not know what happened in part 1, but I know part 2, I'm moving between floors, there's no way in this situation for me to determine whether or not I'm moving up or down. It feels exactly the same in the elevator in this particular part of the motion. I have no way of knowing whether I'm moving fast or slow in the elevator, or sitting stationary on a floor. In a box, and you can't see what's going on outside the box, and you feel net force acting on you, you've no way of knowing whether you're moving at a constant velocity or stationary. This is the same thing as if I put you in a bus traveling down the interstate and I blacked out all the windows, you have no way of knowing whether you're traveling forwards or backwards or how fast you're traveling. You could only probably determine that you are moving down the highway. The third part is the slowing down part. So we get up to the second floor and the elevator slows down. My acceleration now is negative 1.5 meters per second squared. I have to have a downward acceleration to slow down back to 0. So I have weight and normal force, and we can run through the exact same set of math. Sum of forces equals ma. Normal force minus mg equals ma. Normal force equals ma plus mg. Normal force is equal to m plus times a plus g. And so my normal force is 539.5 newtons, something less than what my actual is during this state of motion. So when you get to the top of this elevator, this is where you'd feel that slight feeling of weightlessness when you get up there. The normal force is less than my weight, so I'm going to feel lighter than what I normally am. Now it's worth pointing out if we flipped the elevator around, started on second floor, went down to first floor, part 3 and part 1 reverse themselves. You have a downward acceleration to begin with. That means your normal force is 539.5 newtons on me. And at the end, you have the upward acceleration to slow you down. So the speeding up, slowing down don't really determine the positive or negative. It's whether or not my acceleration is in the positive direction or the negative direction, upward or downward acceleration. So let's look at a second example problem. And in this second example problem, I'm going to have a 50 kilogram crate and I'm going to push it across the floor. The crate initially starts at rest and I'm going to apply a force of 480 newtons on the crate, which is enough to get the crate to move. So basically what that tells me is I have enough to overcome static friction, and the force of friction on the crate as it moves is 450 newtons. So that's the force of kinetic friction acting on the crate. That's a constant if I push the crate. And the two questions I have in this problem is, how long does it take for the crate to travel 5 meters? And how fast is the crate traveling after it's moved 5 meters? So really what this kind of looks like in these two questions is this almost looks like a question from our previous unit, a kinematics type question. How long does it take to move something a certain distance? How fast is it moving after it's moved a certain distance? We do have one piece of information starts at rest that almost looks like a kinematics piece of information. So why don't we try to do this like a kinematics problem? First of all, we're going to look at the forces acting on an object. The object, since I have that information. I have normal force and weight. I have my applied force 480 newtons and frictional force 450 newtons. Those are going to be opposite of one another. And here's the information I know about the problem, or about the situation, and the information I don't know. Now if we look at this, V0 and X, this looks like 2 of the 3 pieces of information I need in order to solve the question. If I'm thinking of this in terms of kinematics, if I knew one of these 3 variables down here, A, T, or V, I could solve for the other 2. Now it happens to work out the questions ask me to solve for T and V. So is it possible to solve A? And the answer is yes, Newton's second law. I have information about forces, I have information about mass. It's possible to pull A out of that information. So my first step in doing this is going to be to figure out what the acceleration is, because if I figure out what the acceleration is, then just do my toolbox of equation kinematics and solve for the 2 things that I'm ultimately looking for in the problem. So in this problem, it never asks for find the acceleration, it asks for time and find the velocity. But in order to find the time and find the velocity, I'm going to need to know the acceleration. So sum of forces ma, the 2 forces that act crate are my applied force 40 newton and my frictional force 450 newtons. Act in opposite direction, so 4A minus 4 is my net force, or 30 newtons. So 30 newtons times 50 kilograms equals A. So A has to be equal to 0.6 meters per second squared. So there we go, I figured out A. What I can now do is do the define T and V, what the was ultimately asking me to find. I can do this equals V0T plus AT squared. I know V0, I know A, so I should be able to solve T. This becomes a little bit here because V0 is 0, so I don't need to do a quadratic here. And now I can solve this equation for T. First step looks like multiply by 2 to get rid of the half and divide by A to get 2x over A equals T. Second step looks like square root everything to get by its 2x divided by A equals T, if I have the root of all that. So something we've already done before. This is in the previous unit. And so if I plug my numbers in, 0.08 the time rate to move 5 meters. So the second question, find V. If I know T and I know A and I know V0, I can find V using this equation. I could also use the 2ax equals, or 2ax plus 0 squared equals V final squared. Also, if I plug in my numbers, the nice thing is this is already solved for V. V0 is 0. A is 0.06 or 0.6, T is 4.08, so the final velocity is 2.45 meters. So in these questions, if it's asking things about kinematics, probably the first thing that you want to do is use the force to find out acceleration. Could also work this in reverse. If I didn't know how hard I was making, and I knew it took 4.08 seconds to push the crate 5 meters, I could use that to work backwards to find A, and then use A to work backwards to find the applied force. That is possible to do this problem in reverse as well. I've just got, because this is the way we would normally see this type of problem in looking at forces. This gives examples of in situations a system is not at equilibrium, or an object at equilibrium. What we'll look at in the next lesson is a specific type of system that seems to come up a lot in physics. And that specific type of system is what's called an Atwood's machine. An Atwood's machine is just a fancy way of hooking different masses that are using strings and pulls. We'll look at that in a lot more detail in the next lesson. In almost every situation when we're dealing with an Atwood's machine, we're dealing with a non-equilibrium problem.